Welcome everybody to the next lecture in the VU model engineering class. Today we will use one running example to introduce you to the practicalities of how actually to create a meta model. A term that has been used by me in the preceding lectures quite often, and we also talked a little bit about that the model-driven software engineering as a discipline offers well-defined also processes how to define meta models, and today we will exemplify how such a process is being conducted. And to better situate meta modeling as a task or as a concept, we will also relate to some historically widely used meta languages in computer science, and this might give you also a point of reference with some of the familiar languages that you are widely using already without considering them as meta languages or meta models. So let's briefly look at some running example. In our class today, we will use a simple UML activity diagram, which has some start elements, some activities indicated in the green color, and some end events. And the question that we would like to ask in this course is how to validate this model. So how could we tell whether this model that has been visualized here on this slide, whether this is valid or not? And the answer obviously in this course is we can only check the validity by considering the meta model. So the meta model is the only source of specification that specifies the well-formedness rules, the constraints, so how many start or end events does such an activity diagram may have, how can I connect different elements with one another. All of those aspects is only specified in the meta model. Yeah? So the message here is, if I only look at the model, I would never be able to validate it or not. Likewise, again, the analogy to software programming, if you only look at the source code, you might never know whether it's valid or syntactically correct or not. You always need to know what is the used programming language. For example, if you know this is a Java program and you know the syntax rules of Java, you could also, by looking at the source code file, verify or validate whether this is correct or syntactically correct or not. Yeah? So the aim of this lecture is to get a clear understanding of what is meant by the term or the notion of a meta model and how are meta models defined, how to create them. All right. So before we go into the details, I also want to introduce the basic components or constituents of what forms a modeling language. Yeah? And there are different aspects that need to be considered to compose what we call a formal language or a formal modeling language. On the highest level, we have kind of semantics. They then define the meaning of the elements in our meta model. So, for example, if we talk about activity diagram, what is the semantics of an activity? What is the semantics of a start event? This needs to be defined, of course. In the best case, formally. At least it should be informally defined using natural language. Then we have the abstract syntax, which defines the language elements, so the grammar that defines the well-formedness rules and defines all of the rules to create models adhering to, or create valid models adhering to this modeling language. And this abstract syntax is then used in twofold ways. One way is to define the serialization syntax, where we talk about how persistency aspects, model exchange aspects, so how can we serialize or deserialize a model. And the other aspect is the concrete syntax, or often also called notation. Here is where we specify how the elements, the language elements that are introduced in the abstract syntax, how they are graphically represented for us humans. Yeah? They can be textually or graphically, like we discussed last week, and this is what we specify and define in the concrete syntax. Yeah? So this slide basically reiterates what I've introduced you. So it introduces the three notions, and we don't need to go into details again. I already told you about that. Good. So let's have a look about a little retrospect or an excursus about meta languages to see similarities and analogies to other languages that we are used to or exposed to as computer scientists, and then to translate this into the meta-modeling aspect and using particularly the meta-object facility. So formal languages and meta languages, they have a long tradition in computer sciences, and they also have, we are also very much exposed to those languages, I would say, without even recognizing that in the first place. And there are major successes like the programming languages in Java and C++, where we always try to specify aspects on a higher level of abstraction, higher level programming languages. Yeah, they were the result of the limitations that we learned about the lower level languages in the first place. So then continuously there was an evolution of the programming languages toward higher levels of abstraction. Yeah? And you see that in the programming languages from C to C++, C#, Java, and so on, Python, TypeScript nowadays. Also to the declarative languages like XML schema, document type definition, RDF, OL, all of those languages are major successful. And the excursus now shows us how are programming languages and XML-based languages defined by means of a meta language, just a little hint and a spoiler, and what can be thereof learned when we talk about meta modeling in modeling language hierarchies. So the famous professors Backus and Nauer invented formal languages and called them so-called meta-languages. And I think all of you should be at least familiar with the Backus-Nauer form or the extended Backus-Nauer form. Yeah? And they were back in the days introduced by those researchers, and they are used until today to specify the syntax, the abstract syntax, and also the concrete syntax in that respect in most of the cases for programming languages, for textual languages. Yeah? So an example is shown here. We have an EBNF, an extended Backus-Nauer form example, where we specify parts of the Java language. So we say Java is composed of, here the corner brackets show us a package declaration, which is an option. So this is optional. You can have, in the beginning of a Java class, you can have optionally a package declaration. Then we have an import declaration, which is also optional, or a sequence. Yeah? So you can have multiple of those, whereas you can only have one package declaration. And then you have a class declaration. Yeah? And then these are just replacement rules. So the package declaration is then replaced by a terminal package. So this word needs to be literally written like this in lower letters, package. And then comes an identifier. And the import declaration is then it's replaced by the terminal import and then also an identifier. And the class declaration is then represented by a modifier. We will learn about this in the next slide. Then we have a terminal class. Then we have an identifier. And then again we have optional, the terminal extends with an identifier that points to a different class. So this is the optional aspect of realizing class inheritance. Yeah? And then we have implements optionally with an identifier for the interface or the interfaces that might be implemented by a certain class. Yeah? And then eventually comes the class body. And here you see these production rules, they show us we have terminals that need to be explicitly like that, all of the bold elements in this figure. And we have non-terminals, that is the other stuff. And the non-terminals are subsequently decomposed until a level where we can have terminals or concrete constants that we will use. So this example a little bit further detailed, where we also have the modifier like public, private, and protected, and we have the identifiers with all of the lowercase and uppercase letters from A to Z, and the numbers from 0 to 9, right? And now if we look at this program in the bottom, we see a package big.tuvin.acat. We have an import statement, import java.util.star, so import everything from the Java util library. And then we have our class declaration where we say public as the modifier, class as the terminal, student as the identifier of our class, then the extends terminal indicating that we extend in a different class, and then the identifier of this different class, which is the class person. Yeah? And then using those two aspects, so the grammar plus the program, enables us to validate whether the program is valid or not against the grammar. Yeah? So this is only possible because we know this, and this is what, of course, also all of the compilers and interpreters are doing back in the back. Yeah? They create the abstract syntax tree, and they look whether the program is valid according to the grammar that it should be used for. Yeah? So if we generalize this and put this into the meta hierarchy that we introduced last time, at the M3 layer, we have the production rules that an eBNF specification is composed of a sequence of rules, and each rule itself is composed of or can be replaced by terminals or non-terminal symbols. If we go one level down on the M2 level, we can then specify one concrete grammar using eBNF. In this example, we used the Java as a language, so we define a Java grammar using the eBNF as a specification formalism, and we define the grammar of the Java language. On the M1 level, we can then define concrete programs using the grammar of Java that we have introduced on the M2 level. So here you again see how this eBNF specification can be mapped into the meta hierarchy that we introduced for the modeling domain in the last lecture. And this bridges and shows what we can then see. Of course, on the M0 layer, we have the execution of the actual program, which is then interpreted by the Java runtime environment. So this was the retrospect, so I'm sure you already knew eBNF. If not, then you should really have a look into this. Very powerful, used until today. And now let's see how we can translate these concepts and these notions into the meta modeling with the meta object facility. So the meta models define the language concepts and the way to specify and provide means to specify what are the valid combinations, well-formed rules. So it defines us the language that we then use to speak, and in the modeling domain, of course, we speak by means of creating models. Yeah? And meta, of course, also is borrowed from the Greek prefix of meta, means something above or about. So a meta model is a model about a model, right? Might sound a little bit weird, but if you look at the example underneath, we see this map of Austria. This can be perceived as a model, and it's using a well-defined meta model which defines that in this map we kind of color code the population. We have some rules and we say there are different ranges, and based on the actual population in a certain area, we color code this area in a well-defined color. Yeah? And you can only interpret this model and respond to the question whether it's valid if you know about the meta model. If the meta model would not be present, then you could just say this looks like Austria, and the color could define some meaning, but it could be air pollution, it could be the population, it could be the density of people living on each square meter, or it could be whatever. Yeah? It could also be an election map or whatever it is. Yeah? So this is the relationship model and meta model, and you should be aware of that. So the advantages of meta models, of course, like the advantages of abstraction that we already introduced, is the possibility to formalize and define a precise definition of the language concepts in a standardized format, where we can that enables us to check correctness and validation or validity of models. It enables us also the management of models in repositories, because the meta models, it's like an XML schema to relate to the XML that we had earlier in the slides. Once you know the XML schema, you know which data formats are expected from the concrete XML documents, and therefore, of course, you can prepare repositories or databases to cope with this schema and with this complexity and structure, or with data that is structured like this. Yeah? Also, metamodels enable us to introduce extensibility. Yeah? So we can define an initial set or a core metamodel that then enables us to do domain-specific extensions, like the example in the last lecture where we had a UML class diagram as a base or core modeling language or metamodel, and then we extended this to the EJB-specific domain, right? Metamodels also enables generalization on a higher level of abstraction, because language concepts for the definition of a metamodel are specified, and one concrete example for that is the meta-object facility, which is a metamodeling language that helps us to specify metamodels. Yeah? And eventually, of course, also very important for this course, we have these tool environments, and now we call them metamodel agnostic tool support. So they are metamodeling platforms, it's what they called often, platforms where you can introduce your metamodel to the platform, and then the platform is capable of generating modeling editors, executing models, creating model transformations and executing them. Yeah. So brief hind, Eclipse Modeling Framework is one of those metamodeling environments, and it's primarily the one that we will use throughout this course in the lab assignments. Yeah, so this is how all the pieces come together and why metamodeling is such a central and valid concept in this course. So let's look at the meta-object facility hierarchy. We again have this 4-layer meta-modeling stack, where on the M3 level we have the meta model, which defines a meta language. In our case, of course, this is the MOF itself, the meta-object facility, or eCore, as the technological implementation of MOF. On the M2 level, then we have an arbitrary number of possible meta models that all use the concepts defined in the meta model. In the example of the UML and MOF, you would say on the M3 level layer we have only one single meta object facility. There's only one. But then there are different modeling languages or different meta models that use the MOF. For example, UML or entity relationships or BPMN. Yeah? And even in the UML, we also have these different diagram types, and all of them conform to the meta-object facility. On the domain engineering aspect, we then have the M1 level, where we actually create models. So again, from one meta model, we can create an arbitrary number of models. For example, concrete UML models for specifying the TU Wien university system or the library database in ER. And then we have on the M0 level model instances. That's a snapshot of the unisystem, for example, or one concrete snapshot of the library of TU Wien, of the Faculty of Informatics, for example. Yeah? So this is how the pieces are fit to one another, and this 4-layer meta-modeling stack is the core concept that we will use throughout this course. And also to situate the modeling tool editors that I mentioned, they would normally come with a meta model implemented already, which is a generic meta model, and then tool meta model engineers or tool developers like you in this course, you will introduce your specific meta model by inheriting from the abstract concepts defined above. And then you can introduce your very domain-specific modeling language and then create editors automatically, so users of your tool can then create models that are valid according to the meta model that you have specified. Yeah? So this is how this concept is executed and brought to life in modeling tool editors. The heart of the meta-object facility is then shown here, where we have classes which are typed, which can be abstract or concrete, which can have superclasses or not. and also have our own attributes, which are again typed elements, which can be read-only or not, which can have a default value, which can be a composite or not, and which can be a derived attribute or not. Yeah? So this is at the core of the meta-object facility. In the background there's much more, so please have a look at the standard to learn more about this, but it's not the purpose now to introduce all of those different notions in detail. Rather, in this lecture, I want to discuss with you about the development process of a meta model. So how do I actually create such a meta model? And this is a three-step approach. In the first step, we have a modeling domain analysis, where the purpose is, or the goal is to identify and define the purpose, the realization and the content of a modeling language, and you can achieve that by creating first sketches of reference modeling examples. So this sounds maybe a little bit weird, but basically what is meant by that is that you actually use pen and paper or PowerPoint and you sketch example models that you would like a meta model to be able to allow. Yeah? So you would specify a representation that you would like to have, and then you kind of think about in a subsequent step, in the modeling language design step, how would a modeling language need to look like to allow that all of the sample sketches that you have created are valid models according to this kind of meta model. So you formalize the modeling language by defining actually a meta model like the one that we saw with the EBNF, or using a different formalism, for example, using the meta object facility, and then defining your meta model as an instance of the MOF. Additionally, you can define some constraints. So these are some well-formedness rules that limit the allowed combinations, for example, of different elements, or that prescribe what are the minimum or the maximum number of instances of certain concepts in a model to be valid. Yeah? We will go into that later on in the running example. Eventually, we have the modeling language validation step. So here you instantiate the meta model to look if you can actually recreate the reference sketches that you have created in the first place. You maybe also expose your meta model and your tool to users, and you collect feedback and see whether or not they are satisfied or not, whether or not the meta model is expressive enough to cover all of the different models that you would like it to cover or to represent or not. And this, of course, then leads to a new iteration. So you have new domain models which are currently not valid according to the meta model. So you start again with these models, and you go into the second phase, and you have a modeling language redesign kind of. Yeah? So it evolves based on the evolving requirements and the lessons learned from executing and using the the current meta model. So this is an iterative process, of course, although it's visualized as a sequence. So let's go back to our running example, and let's now really look at how would a meta model look like, and that is the question. So how does a possible meta model for this modeling language look like? And then we follow this three-step approach in a stepwise manner, and we try to abstract from the different concepts. So first of all, if we look at this model, we can create something that is called a notation table. So we just generalize all of the elements that we see. So we have a dedicated set of unique elements. The one is the activity diagram as a whole that has a name on the top left side of it. We have something like a final node, which is a circle with a thin circle surrounding it. We have an initial node, which is a filled circle. We have some means of an activity where some name is present in the center of it. And we have some transition that seems to connect two activities or start and end events or nodes with the activities. Yeah? So those are the unique elements that we can generalize from this one model. So all of them need to be present in the meta model, obviously, because anything that is not present in the meta model cannot be present in the model, right? If it's not predefined in the meta model, you cannot use it in the model. So let's try to formalize this a little bit. So what would be the concepts and the properties that we would use if we translate this into a kind of an object-oriented notion? So we would have the concepts of an activity diagram, final node, initial node, activity, and transition. They have some intrinsic properties. We already mentioned that the activity diagram and the activity, they have a property of a name to indicate some semantics. And they also have some relationships to other elements. So the activity diagram has a relationship to an initial node, to a final node, and seems to be an unlimited number of activities and transitions. That's already an assumption. You could also say, from this one instance, I assume every model will have 3 activities. Could be, yeah? So this is what we specify now, and what we then give to users and see, okay, maybe users want to have the flexibility to have activity diagrams with 2 activities or 10, and then we might have learned, okay, maybe it's best to do this unlimited. Yeah? So this is what I mean. It's a design process that takes place now, and you as a meta modeler, you need to think very well how potential users would use your meta model and which flexibility you would like the meta model to have. Whereas in some aspects you don't want it to be flexible, but you want to be very precise and very concrete in what is allowed and what is not allowed. We'll come to that. We have some final node that has, it seems, an incoming transition, and an initial node that seems to have only an outgoing transition. We have an activity that has incoming and outgoing transitions, and the transition itself seems to be valid between source and target node, which are initial node, final node, or activity. Yeah, so this is some basic rules that we can derive from looking at this one single model. So how would this then look like in the MOF way of thinking? In the MOF way of thinking, we have the concept of a class and the concept of a property. So we would translate those initial elaborations into the world of the meta-object facility. So we would realize every concept as a class, and the intrinsic as well as the intrinsic properties as well as the relationships would be realized as properties. A meta-model sketch of our current conceptualization, I would call, from the domain, is that we have an activity diagram which has a property name. And this activity diagram is composed of one initial node, one final node, one or many transitions, one or many activities. And activities can be connected with transitions by incoming and outgoing relationships. And a final node can only have an incoming transition, whereas an initial node can only have an outgoing transition. Yeah? So this is the current conceptualization, and then we can use this to create sample models. So on top you see the meta model. We used color coding to map the instances to the meta model concepts. And now on the model level you see we used a notion that is similar to the object diagram in UML. So we have the unique identifier and then a double point with the type of the concept that we instantiate. So we have an activity diagram with the name coursework that has a transition to an initial node, which has a transition to an activity, which is called attend or something, abbreviated attend lecture, which has a transition to study content, which has a transition to write exam, which has a transition to the final node, which then composes our activity diagram. On the middle area, we see this as an object diagram using the abstract syntax, so only rectangles are used. And on the lower area, we use this, we represent the same model using the concrete syntax. So here you also nicely see the differentiation between the abstract syntax, which is more generic and machine readable, versus the concrete syntax, which is what we primarily as human beings require to understand the model very easily and to grasp the semantics that are encoded by this model. Now, assume we do some changes on the metamodel. Like I said, metamodeling is an iterative process, and metamodels evolve with the requirements of our domain. So let's assume we delete the class activity, we add the class an abstract or a generic class node, we add the class activity node, and we delete also the redundant references that we have in our metamodel. So you see already the metamodel now seems to be much more compact, while actually allowing the creation of the same models. In addition to that, we define some OCL constraints. So this is what I meant. When you consider the metamodel design, in this process you might want to have aspects that you want intentionally to be flexible, while other aspects you intentionally don't want to be flexible. They need to be fixed in order to make sure that only valid models, semantically valid models, are created. So for example, you could say, in the context of an activity diagram, don't worry, we will talk about OCL in the coming lectures, but just a heads up. In the context of an activity diagram, you define two invariants, so rules that always need to hold true, where you say there should be at least one initial node and one final node. So in the set of all of the nodes, so self.nodes, if the context is activity diagram, you would say in the activity diagram.nodes, so in all nodes of this one diagram, there should be one initial node and at least one, or exactly one, final node. In the context of a final node, you further specify the invariant that self, so final node.outgoing.ocl is undefined. So you would define that for a final node, it is not allowed to have any outgoing relations or references. On the contrary, for the initial node, you define that there might be no incoming relations. Yeah? So the initial node of an activity diagram may not have any incoming relationships. And finally, for the activity diagram, you could say the name of an activity diagram shall not be empty or undefined, right? And these are some constraints that you define again on the metamodel level, and they are then evaluated by the tool environments on the instance level. So for each model that you would create based on this metamodel, you can then evaluate whether or not the constraints hold or whether or not they are violated. And if so, you can give the modeler a hint and say this constraint is violated, so the modeler learns where to fix this. So let's see what happens if we already have our initial model that we introduced previously, but now the metamodel has changed as discussed. Once we would now execute the validation, the tool would immediately recognize some issues. For example, the class activity is now not known anymore. So the metamodel on top doesn't have a notion or a concept of activity. So the tool cannot infer this, yeah? Right? At the same time, the references to initial node, final node, and activity are unknown. So the tool cannot infer this because the metamodel is not valid anymore according to its metamodel. So what we would need is, of course, to do some co-evolution. So when the metamodel evolves, we also need to learn about these evolving steps, and we need to make sure that we apply certain rules also on the model level to transform, and now we are already in the domain of model transformations, to transform our model, which is currently invalid against the new and the evolved metamodel, toward becoming valid again. And there are different types of how we can do that. For example, we can do some typecasting, so we can say we cast any activity objects to activity node objects, and also we can cast any initial node, final node, and activity links to this generic notion of a node. And then when we apply this, we see here the new object model on the lower area, where we now use the activity nodes, and we use initial node and final node, and all of them are nodes. And then we see that this model is again valid according to our evolved metamodel. So this is using a running example, you should now have a better understanding of how meta-modeling is conducted, what is the purpose of meta-models, what is the challenge. So it's not that easy to define this language on a generic and abstract level to account for all of the different instances and expressivity you want to have. So this is why metamodeling is very challenging, while at the same time you should also be now aware about the power that comes in the definition and specification of languages that are tailored to your specific domain and to fulfill your specific purposes. Yeah? In the subsequent lectures, we will talk about the Eclipse modeling framework and how to use this framework to realize your meta models and to automatically generate model editors and code model execution environments for your well-defined meta models. Thank you very much.